Section: Introduction. We're going to delve into the world of fine-tuning language models, which is a technique that can significantly enhance performance across a range of natural language processing tasks. However, this method has a downside. It requires updating and storing a large number of parameters, which can be quite costly, especially when dealing with models that have hundreds of millions or even billions of parameters. An alternative approach, known as prompt engineering, doesn't require any parameter updates, but it's typically challenging to design and can yield inconsistent performance. As a result, there's been growing interest in methods that are more efficient in terms of parameters, aiming to learn only a small number of parameters per task while still delivering performance comparable to full fine-tuning. One such method is prompt tuning, which adds trainable continuous prompt vectors to the input. This method stands out because it delivers competitive performance with fewer trainable parameters and doesn't drastically increase its trainable parameters as the model size grows. However, it does have two significant limitations. It often converges slowly and is sensitive to the initial setup, and it extends the total length of the input sequence, which increases computational demands due to the quadratic complexity of the transformer. Recent studies have proposed variations of prompt tuning to address the slow convergence issue by initially pre-training soft prompts on a variety of source tasks. This is known as parameter-efficient transfer learning. Some studies also improve performance by jointly training learned prompts from these source tasks on multiple target tasks. However, the issue of increased computational load due to the extension of sequence length remains largely unaddressed. In this paper, we propose a new method called Decomposed Prompt Tuning, which breaks down a trainable soft prompt into a shorter soft prompt and a couple of low-rank matrices. The multiplication of these low-rank matrices is then added element-wise to frozen word embeddings. This shorter soft prompt and the updated word embedding matrix are then optimized using two different learning rates, which is a crucial step for model convergence. Our experimental results on 23 natural language processing and vision language tasks show that decomposed prompt tuning outperforms the state-of-the-art parameter-efficient fine-tuning approaches, including the full fine-tuning baseline in certain scenarios. Our study empirically shows that decomposed prompt tuning significantly improves the training efficiency across various model architectures and sizes, saving more than 20% in both training time and memory costs compared to the original prompt tuning. Importantly, decomposed prompt tuning becomes increasingly efficient as the model size grows, making it particularly advantageous and suitable for large language models. Furthermore, our additional analysis in the few-shot learning setting reveals the compatibility of decomposed prompt tuning with parameter-efficient transfer learning approaches. In summary, the main contributions of this paper are as follows. 1. We propose the decomposed prompt tuning method, which addresses a key efficiency limitation of prompt tuning by decomposing its soft prompt to reduce input sequence length. Decomposed prompt tuning significantly improves the training and inference efficiency, reducing both time and memory costs by over 20%. 2. Our comprehensive evaluation on 23 natural language processing and vision language tasks demonstrate that decomposed prompt tuning outperforms state-of-the-art parameter-efficient fine-tuning approaches, including the full fine-tuning in some scenarios. Additionally, our experiments show that decomposed prompt tuning smoothly integrates with parameter-efficient transfer learning approaches, and the advantage of decomposed prompt tuning persists in the few-shot learning setting. 3. We empirically show that decomposed prompt tuning becomes increasingly efficient as the model size grows, making it particularly well-suited for large language models. Furthermore, decomposed prompt tuning is orthogonal to various parameter-efficient fine-tuning approaches and can be easily combined together. Now, let's revisit the background of prompt tuning. Given a set of n-labeled training data for the target task, each input text is mapped into an associated sequence of word embeddings. Prompt tuning appends a trainable prompt matrix to the frozen word embedding matrix, where the number of virtual tokens is a hyperparameter. The soft prompt can be initialized either randomly or by sampling word embeddings from the top vocabularies. Consequently, the model's input becomes the combined matrix. The targeted loss function is then formulated, where the loss function is only optimized with respect to the soft prompt matrix. Section Summary. In this section, the authors introduce the concept of prompt tuning, PT, which involves appending a trainable prompt matrix to the input of a language model. They propose a new method called Decomposed Prompt Tuning, DEPT, which decomposes the soft prompt into a shorter prompt and low-rank matrices, resulting in improved training and inference efficiency. Experimental results demonstrate that department outperforms other parameter-efficient fine-tuning approaches and is particularly advantageous for large language models, LLMs. Section. Our approach. Decomposed Prompt Tuning, Department. Our method, known as Decomposed Prompt Tuning, Department, differs from the standard prompt tuning, PT, approach in terms of inputs. We break down a trainable prompt matrix, which is usually used in standard PT, into two parts: a smaller trainable prompt matrix and a pair of low-rank matrices. The smaller matrix is added to the word embedding matrix, similar to the standard PT method. The pair of low-rank matrices, on the other hand, is used to update the word embedding through a coordinate-wise sum. In this process, the low-rank matrices are trainable, while the word embedding matrix remains fixed and does not receive updates during training. We initialize the first low-rank matrix with random Gaussian values and the second one with 0, so the update to the word embedding is 0 at the start of training. In our experiments, we choose the dimensions of the smaller trainable prompt matrix and the low-rank matrices in such a way that the total number of trainable parameters remains the same as in the standard PT method. This design choice improves memory efficiency and reduces computational cost compared to the standard PT, as the shorter input sequence length significantly reduces computation due to the quadratic complexity of the transformer model. Our training strategy also differs from the standard PT method. We train the smaller trainable prompt matrix and the pair of low-rank matrices at different learning rates, rather than using a single learning rate as in the standard PT. The learning rate for the smaller matrix is typically much larger than that for the low-rank matrices. In the following sections, we will present our experimental setup and results. We will compare the performance of our department method against state-of-the-art prompt embedding fine-tuning, PEFT, approaches and full fine-tuning across 23 different natural language processing, NLP, and vision language, VL, tasks. We will also compare the training, inference time and memory cost of department with the standard PT. We evaluate our department method on 21 NLP tasks and 2 VL tasks using various datasets sourced from the GLUE benchmark, SuperGLUE benchmark, MRQA 2019 shared task, and other datasets. For VL tasks, we experiment with the visual question answering task and the image caption generation task. We compare department with a variety of baselines, including fine-tuning, the standard PT and its variants, and state-of-the-art PEFT approaches. For a fair comparison, we use the same performance metrics from published papers and use the T5BASE model as the backbone for all these baselines. In our study, we mainly use the T5BASE model and set the number of virtual tokens as 100 across all tasks for the standard PT. We adjust the hyperparameters of department accordingly to maintain the equivalent number of trainable parameters. For VL tasks, we use the CLIP T5 architecture, which combines CLIP and T5BASE with the CLIP frozen. We also extend our evaluation to include smaller and larger versions of the T5 and GPT-2 models. In the few-shot experiments, we randomly select a certain number of examples from the training set and report the mean and standard deviations for each experiment. We use 5 source tasks to initialize our soft prompt and low-rank matrix pairs. More details about the hyperparameters and implementation can be found in the appendix. Section Summary. The authors propose a method called Decomposed Prompt Tuning, Department, that decomposes the trainable prompt matrix in prompt tuning, PT, into 2 components, a shorter trainable prompt matrix and a pair of low-rank matrices. This decomposition improves memory efficiency and reduces computational expense compared to PT. Additionally, department uses 2 different learning rates for training the shorter prompt matrix and the low-rank matrices, which is shown to be important in their experiments. Section. Main results. In this section, we present the empirical evidence that supports the effectiveness of our proposed method, department, across a variety of 23 natural language processing, NLP, and vision language, VL, tasks. We have conducted experiments on GLUE and SuperGLUE benchmarks, MRQA 2019 shared task, 4 other NLP datasets, and 2 VL tasks. The results of these experiments are presented in 3 tables. We also provide a visual representation of the model's performance in relation to the number of trainable parameters on the glue and superglue benchmarks, which can be found in the appendix's figure. Our experiments have led us to two main conclusions. First, Department consistently performs better than the standard prompt tuning, PT, and its prompt enhanced transfer learning, PETL, variants. Second, Department achieves competitive or even superior performance compared to the best prompt enhanced fine tuning, PEFT, methods, while using fewer trainable parameters. Let's delve deeper into these findings. Number 1. Performance on glue and superglue benchmarks. Our results show that Department outperforms top PEFT methods, such as adapter, LoRa, and LST on the glue and superglue benchmarks, while using fewer trainable parameters. Notably, Department also surpasses the full fine-tuning baseline on both benchmarks. Furthermore, Department performs better than standard PT and all its variants that incorporate additional transfer learning and multitask learning. For instance, Attempt, which requires additional pre-training of the soft prompt on the source tasks, achieves an average score of 83.4 on the glue benchmark and 70.5 on the superglue benchmark. In contrast, Department surpasses Attempt with scores of 85.9 and 76.5 on glue and superglue, respectively, despite training fewer parameters. Department also outperforms MPT slightly on both benchmarks, without using additional transfer learning or multitask learning. These results were achieved with less training time and reduced memory resources, which validates the effectiveness of our proposed method. It's worth noting that Department can be used in conjunction with these PETL approaches. We will explore the compatibility of Department and PETL in a few-shot learning setting later. Number 2. Performance on MRQA 2019 shared task and other NLP datasets. Our results show that Department significantly improves the average performance of the standard PT on the MRQA 2019 shared task and 4 other datasets. Department outperforms the PT variants that use additional transfer and multitask learning, without adding extra trainable parameters to the standard PT or relying on any PETL approaches. While DEPT's improvements over the standard PT and its variants are promising, there is still a performance gap when compared to the full fine-tuning baseline. Future research could explore ways to combine Department with other PEFT methods, such as LoRa and adapter, to narrow this performance gap. Number 3. Performance on vision language tasks. Our results show that Department, while updating fewer parameters, achieves a CIDR score of 113.7 on the MS COCO caption generation task, outperforming top PEFT approaches. This suggests that our proposed method is effective. However, while Department performs better than methods such as p-tuning and bitfit on the VQA dataset, it still falls short of the full fine-tuning performance. This suggests that in certain tasks, using a greater number of trainable parameters could be beneficial. Time and memory efficiency. We provide empirical evidence supporting the efficiency of our proposed method Department across various model architectures of different scales on the glue benchmark. To ensure a fair comparison, we kept the number of trainable parameters in Department the same as that in the standard PT. As a result, once we choose the length of the soft prompt in Department, the rank of the low-rank matrices becomes deterministic. In our experiments, we primarily compared Department with the standard PT using 5 different lengths of soft prompt. We provide a visual representation of the average glue performance of Department, along with the associated training, inference time and memory cost compared to the standard PT. Section Summary. The empirical evidence presented in this section supports the effectiveness of the proposed method Department across various NLP and VL tasks. Department consistently outperforms vanilla PT and its PETL variants, achieving competitive or better performance than state-of-the-art PEFT approaches while using fewer trainable parameters. Additionally, Department demonstrates efficiency in terms of training time and memory resources compared to the vanilla PT. Section Number 1. Department improves time and memory efficiency up to more than 20%. We found that our method, Department, can enhance time and memory efficiency by over 20%. We compared DEPT's performance, training time, and memory usage on the glue benchmarks against different lengths of soft prompts. We used both encoder-decoder, T5, and decoder-only, GPT-2, models across 3 different sizes. Our results showed that breaking down the soft prompt into a smaller soft prompt and low-rank matrices can improve performance while also making training more efficient and reducing memory usage. For instance, using a soft prompt length of 20 with the T5 model in department led to better performance on the GLUE benchmark than the standard PT, while also improving training efficiency and reducing memory usage by about 25%. This was also true when using the GPT model. However, we noticed a significant drop in performance when the soft prompt was removed and the model relied solely on the pair of low-rank matrices, regardless of whether we used T5 or GPT-2. We also found that department becomes more efficient as the model size increases. We measured inference speed by the average number of samples evaluated per second on the GLUE benchmark using a single RTX 3090 GPU. The relative improvement in the number of inference samples per second over the standard PT increased as the model size increased. For example, with the T5 SMALL model, the standard PT evaluated 167.3 samples per second, while department evaluated 178.3 samples per second, a 6.5% increase in inference speed. When we used the T5 LARGE model, the standard PT evaluated 21.0 samples per second and department evaluated 24.8 samples per second, an 18.1% increase in inference speed, a significant increase from the previous 6.5%. This suggests that department is particularly useful and more applicable in the context of large language models. However, both the standard PT and department often underperform in few-shot learning tasks. To address this, we used a transfer learning method inspired by recent PETL studies. In the context of few-shot learning tasks, we pre-trained both the soft prompt and the low-rank pair on source tasks before moving on to the target task. We tested DEPT's effectiveness in few-shot experiments across 14 NLP tasks, with 4, 16, and 32 training examples. Our experiments showed that department integrates well with PETL approaches and can achieve competitive or even better performance than state-of-the-art PEFT approaches in the few-shot learning setting. We compared DEPT's effectiveness with various PEFT approaches in few-shot experiments, including full fine-tuning, FT, adapters, AD, standard PT, PT, spot, ST, high performer, HF, attempt, ET, and MPT on Boole Q, CB, and SciTail datasets. Our results showed that the standard PT struggles with few-shot tasks, highlighting the importance of PETL for the PT in few-shot learning tasks. However, DEPT's performance greatly benefits from the PETL framework. For example, while the standard PT achieved an accuracy of 53.5% on the SuperGLUE CB dataset and 57.7% on the SciTail dataset with 4 training examples, department with PETL achieved an accuracy of 75.0% on the SuperGLUE CB dataset and 78.1% on the SciTail dataset with the same number of training examples. This supports our observation about the compatibility of department and PETL approaches. Furthermore, department with transfer learning achieved comparable performance with the variant of the PT, MPT across 14 NLP tasks. Notably, department outperformed all other variants of the PT, i.e., spot, attempt, and other PEFT approaches, demonstrating our method's effectiveness. Section summary. The department method improves time and memory efficiency by more than 20% on the GLUE benchmarks, using both the T5 and GPT-2 models. By decomposing the soft prompt into a smaller prompt and low-rank matrices, department achieves comparable or better performance while significantly enhancing training efficiency and reducing memory usage. Additionally, department becomes more efficient as the model size increases, resulting in a boost in inference speed of up to 18.1% for larger models. However, department, like vanilla PT, faces challenges in few-shot learning tasks, but it can be effectively combined with PETL approaches to achieve competitive or better performance than state-of-the-art PEFT approaches. Section. The importance of different learning rates. Let's delve into the significance of varying learning rates. Our experiment results, derived from 3 different learning rate settings, highlight this importance. We trained the soft prompt using a pair of low-rank matrices in 3 ways. 1. We used a single learning rate of 0.3. 2. We used a single learning rate of 0.0005. 3. We applied mixed learning rates, where the soft prompt was trained at a higher rate and the pair of low-rank matrices at a lower rate. In our tests, the first method achieved an average score of 40.8 on the glue benchmark. The second method showed an average score of 54.7, while the third method significantly improved the average score to 85.7 on the glue benchmark. These results underscore the effectiveness of training department with two distinct learning rates. Now, let's talk about parameter-efficient fine-tuning. Unlike standard fine-tuning and prompt-based fine-tuning, which update all parameters, parameter-efficient fine-tuning, PEFT, methods have shown impressive performance across various tasks while only updating a limited number of parameters. Several techniques fall under PEFT. For instance, adapters and its variants, hyperformer and compactor, add new trainable modules to each transformer block of the T5 model. BitFit only updates the bias parameters, but it tends to underperform on larger networks. Prefix tuning adds a soft prompt, parameterized by a feed-forward network, to the model input. Diff pruning learns a sparse update of a neural network's weights but uses more memory. Fishmask also performs sparse updates but is computationally demanding and inefficient on modern deep learning hardware. LoRa uses a simple low-rank matrix decomposition to parameterize the weight update. Other methods include EA, B-group color, table brown, cubed E-group, which scales activations by learned vectors for few-shot learning, and LST, which operates a small transformer network on the side of the pre-trained network to reduce training memory. Prompt tuning, PT, adds a trainable soft prompt to the model input embeddings. Compared to other PEFT methods, PT uses fewer trainable parameters, which do not increase as the model size grows. There's also a method that combines prefix tuning, adapters, and LoRa through a gating mechanism. Department can be applied to this method and can be easily integrated with other PEFT approaches. Let's now discuss transfer learning for PT. Several recent studies aim to enhance PT's performance through parameter-efficient transfer learning, PETL. PPT seeks to boost PT's performance by further pre-training, which requires task-specific designs and significant computational cost. Other methods improve PT through prompt transfer across different tasks and models. Spot uses a single prompt, chosen based on a similarity measure, but requires a massive search. Attempt uses an attention mechanism over the source prompts to initialize the prompt for target tasks, but it requires extra parameters. MPT applies a shared soft prompt across different tasks, but its effectiveness for a wide range of source tasks is untested. It's still a matter of debate whether a diverse range of tasks can effectively use a single prompt to share all knowledge. Previous studies may have overemphasized the role of transfer learning and multitask learning in enhancing model performance when extensive labeled datasets are available. It's important to note that the main advantage of PETL for PT is to speed up training convergence and improve model performance, especially in the context of few-shot learning.